I hope everyone's doing all right at home and staying safe in the midst of all the chaos. I'm going to explain a little bit about the Neff reaction today. So this was discovered by John Ulrich Neff, I believe, who discovered this in 1894. This is like his big work of his life. So I'm going to explain to you the overall mechanism here and the sort of character of the starting material. And then I'll explain a little bit about the preparation of how you make the starting material. And I will go into just a little bit of detail, not a whole lot, because that goes a little bit beyond this reaction. And then I'll explain the mechanism and the limits here. There's a couple different kinds of mechanisms for this reaction because I don't believe it's fully agreed upon what a certain portion is, and you'll see what I mean. And then I'll explain briefly sort of modifications that are done in certain cases, but I won't go into a huge amount of detail about modifications because there's a huge number of modifications you can do, and it's just it's a lot to take in at once. So the Neff reaction is done to convert essentially a nitro group to a carbonyl. In some cases, though, you can prepare the nitro group so it could act as an intermediary for something else. So keep that in mind. That's why I think it may be useful. But we have, in essence, we have a nitroalkane salt. Looks a little bit like this. Keep in mind, one of these R groups can be a hydrogen. So this can be either a primary or a secondary nitroalkane salt. And what you're going to do is, in general, you react it with a base first, and then with an acid. These two, it sort of varies across literature. I'm going to focus here in particular with sodium hydroxide and sulfuric acid, but there are cases in the literature where they discuss sodium methoxide and methanol in the same pot, so that could make it a little bit easier for the reaction to occur. But that's also with some specific compounds. It's there's a lot of information with this reaction, so I want to try to keep us grounded and basic and simple so that we can get the basics, and I'll touch on some of these modifications in the end. But anywho, you mix these two reagents with the starting material, and what you'll get out is you'll get a ketone or an aldehyde, depending on what the R groups are, and nitrous oxide and water. These two components here we'll talk about more, but just keep in mind that these two bits here are important to think about going forward. So overall mechanism, we start with a nitroalkane salt. We use base acid. We get a carbonyl group, either a ketone or an aldehyde. To get this nitroalkane salt, there's a couple different ways we can do this. Perhaps the simplest way to approach this is you can have an alkyl halide. Again, this goes a little bit beyond Neff, but it's useful for us. Plus silver nitrate. So if I want to get a nitroalkane, I might do a substitution reaction here. I'm going to get a nitroalkane. Again, this would be substitution reaction. A nitroalkane, in order to get a salt, the easiest way to do this, as far as I've read online and literature-wise, you want to employ a sodium hydroxide again, so to deprotonate and get the salt. You want something that's going to really be a very strong base because the hydrogen or the proton involved has pretty high pKa. I think it's like 16, 17 or something. But you also want to make sure that this nitroalkane is either primary or secondary substituted, because we need one hydrogen in order to do this whole process. And I'll explain sort of what I mean by that.
Hopefully you can see. Start with the nitroalkane right here. And the first step is going to involve the base. And let's just use NaOH right here. And this is going to be a one direction step. There's going to be a hydrogen here that the hydroxide is going to come grab that hydrogen. This bond's going to jump up there, and this double bond is going to jump up onto onto that oxygen. And then so we're going to end up with this molecule right here. And then, so that's the first step with our base. And then the second step is going to involve an acid. Here, we'll just use a hydronium ion, but, it could be, any sort of dilute acid in water. So, let's start here. We'll separate that. This is our acid step. Okay, so we're going to have two proton transfers here from our hydronium ion. It's going to come down, grab hydrogen, and that's going to happen over here as well. I'm not going to draw it out, but there's two proton transfers. And that will bring us to this molecule. Going to have two OHs right there. And then we're going to get a nucleophilic attack from a water molecule. Like we said, it's dilute acid in water. It's going to come attack there at that double bond carbon to that nitrogen. This is going to jump up, and we're going to get, make sure you can still see it, yep. And we're going to end up with a tetrahedral intermediate. That looks something like this. So now that positive charge on the nitrogen's gone away. Okay, we're going to get a proton transfer here. End up with this. Still in the tetrahedral intermediate, by the way. So the proton transfer there was that proton getting grabbed by probably water acting as the base here. And then this nitrogen is actually going to take a hydrogen from, one of our acid molecules here. It's hydronium. So it's going to come in, grab that. It's going to jump back up there, make the water. And that will give us, I'm going to draw it down there, down here so you can see. Actually, I'll switch paper so I can do it bigger. Okay, so then, let me just make sure you can still see it. Yep, okay. And that will give us this right here. And so this is the kind of controversial step. There's different literature thinks different things about how this actually happens, but from our research, this is kind of the most agreed upon mechanism for the Neff reaction. Okay, and then so from here, we're going to get a water. This, we're going to lose a water, and the mechanism for that is going to be this water, this OH is going to leave right here, but it's also going to grab this hydrogen, which is kind of interesting and something that we haven't really seen. And then this bond right here, this hydrogen bond, is going to go down there and create a double bond. So after that step, we're going to lose a hydrogen, minus H2O, and we're going to have something that looks a little bit like this. Positive charge right here. And then what we're going to see happen here is this part of the molecule is going to leave. We're going to get a lone pair from this oxygen, jump down there. That's going to jump back up there. This is going to leave, and that'll give us something that looks a little bit like this. We're starting to see that ketone form. It's going to be OH. It's going to be a positive charge, and then we're going to get a proton transfer. That hydrogen is going to get taken away, and this will give us our ketone. And again, this can be a hydrogen, so this also works with aldehydes. It'll also yield an aldehyde, and so this is our main product. But as we talked about before, we're also going to get nitrous oxide, which is this, and water that we saw leave. And how the nitrous oxide is going to form is this molecule right here, this HNO, is going to dimerize with another HNO molecule. It's going to give us this dimerization, and then this molecule right here will form the nitrous oxide and some more water. Now, I'll let you look at that mechanism right there, but I just want to point out that this is the main product. And again, it works with primary or secondary, so it'll yield a aldehyde or a ketone from that starting nitroalkane. Okay, great. And if you have any questions, just reach out to Andy, Aiden, or I, and we'd be happy to get back to you.
Okay, so I want to just briefly talk about some of the modifications you can do. Whenever you have different R groups, you're going to want to be mindful of different side reactions, especially since the reagents you oftentimes use are acids and bases. I mean, they are bases and acids. There's varying strength of the harshness of the reagents. Sometimes it's sodium hydroxide and sulfuric acid. Other times we get weaker acids and bases. It seems to differ depending on what the R groups are. What I'm trying to get at, though, is that we must be mindful of the protons involved. You want to think about alcohol groups, whether a protecting group might be added. You want to think about ketones and about your alkynes involved. So these are the different components that are involved. Of course, there's a lot of modifications. I can't go into all the modifications in just 15 minutes, but there's some that use oxidizing reagents. There's some that use reducing reagents. One of the big popular ones is to add titanium trichloride to the mixture at a certain point as an oxidizing reagent, and that's good for ketones and alkyne groups. But what I'm trying to get at here, what I hope you'll take away from this whole thing, is that we can start, if you really are interested, you can start with an alkyl halide, as I discussed a while ago, and you can go to a nitroalkane salt. I talked about this in preparation. And then you can take that, and it'll go through what's called a nitronate ion, which is after that base. And then we'll get either a ketone or aldehyde with the acid. There are modifications on this, and I recommend you look them up if you're really interested in using this in your synthesis, but I think that this in and of itself is already illustrating the utility here. And I hope you'll keep this in mind, and I hope that everyone can enjoy going outside as much as like on a walk once in a while. I mean, I know that we're going to be trapped inside for a while, so I hope that this is helpful, and thank you for listening.